do this using calculus. Let's begin. So, in order to begin, let's go over a couple of conditions of why we can't use Gauss's law. Now, the first thing that we should do is we should just draw the scenario here. So here I have a XY coordinate plane, and I'm going to say that my rod will be somewhere along here. Okay, and for the sake of the future, we'll say that this rod has a length of L. And from the origin, it is a distance of A far away from the origin point. Okay. Also, this is a positively charged rod. So what I want us to find is I want us to find the E field at the origin. So E field at origin from positive rod. Okay, so you might be tempted here to use Gauss's law, but remember, you can only use Gauss's law if there is one symmetry from your E field. And in this case, we learned that the symmetrical E field emanates from the sides of the rod. So along here and along there. Okay, but for this problem, we don't care about that part of the E field because we want to know how this end of the rod affects, or how the end of the rod creates an E field at the origin. And so if it's positively charged, we know that at the end of the rod, there's going to be E field pointing to the left. And so we can't create a Gaussian surface that has a uniform field through it to just encapsulate that E field. So Gauss's law is out. All right. Now, if you're used to the ease of Gauss's law, this one's going to be a little bit trickier because there's a little bit more thinking involved, but I know you all can do it. All right, so let's begin. In order to fully understand this situation, what I want us to do is, before we go into the calculus, I want us to break down exactly what our formula means when we are looking at it through the lens of calculus. So if I were to have a very similar scenario, but instead of a cylinder of charge, you copy this down, we have instead a single point of charge there, where the dimensions are still the same. This is still a distance A away. So if I have a single point of charge right there, that point of charge will have a E field at the origin pointing to the left, like so. Okay. Now, here's the idea of calculus. We are not working with a single point of charge because we already did that, right? We know that single point of charge, we will get a formula of kq over r squared, and we just plug in the variable so we can find what the E field magnitude is at that point. But here we have a rod of charges. So the idea is we have a single point of charge there, and what we're going to do is we're going to add another single point of charge right next to it. So when we do that, there's two things that are happening. We are increasing the amount of charge, and so when we are increasing the amount of charge, that's what we call the dq. So let's write down what this means. This dq represents the amount of charge that we are adding to create, I'm going to put this in quote, create the shape, all right? And so the shape is whatever we're starting off with, and in this case, it'll be a cylinder. So if we're continually adding up tiny bits of charge, those tiny little bits of charge is what we call dq. And so whenever we add a tiny bit of dq, what we're doing is from this second tiny bit of charge, let's make this tiny bit of charge. Let's change the color. Let's make it green. All right, so if we add a tiny bit of charge there, that tiny bit of charge is going to create an E field, but it's going to be slightly weaker because it's a little bit further away. But overall, the net E field will increase. I'm going to do this in, let's do this in nice light blue, and I'll make it a little bit bigger. So the net E field from the green and the red, it'll create a E field that is slightly bigger. Okay, so this is going to be the net E field from those two charges. Okay, now what we're doing there is we are adding up the individual E fields. And so when we're adding up tiny bits of E fields, we call that dE. So dE is the resultant field from the dQ. So the idea here is as we're adding tiny bits of charges, we are also increasing the E field ever so slightly. And if you do this enough times, we should get, I'm going to go back to red. Okay, we add up all these charges in a line. Okay, we add up enough of those, and we will get a cylinder of charge. And that's what we see above. All right, so now that you know the theory behind this, let's actually get to the calculus and the math. All right. Now, to start off, we actually start off with the same formula. E is equal to KQ over R squared, right? That's our base formula. But what I want you to always do is I want you to start off with the calculus version of this, okay? We are adding up tiny bits of charges, tiny bits of field, because we have tiny bits of charges as our distance is changing, right? Now from there, what we can do is we can integrate both sides. So what this integral symbol means is that we are adding up all of these E fields, okay? What this dQ means is that we're adding up all of those tiny charges. It's a summation. So if we take the integral of dE, we're just left with E here, and we're left with this right-hand side looking a little bit like this. All right. Now, there needs to be a vector here because E field is a vector. So what I'm going to write here in parentheses is that our E field is pointing to the left. It's always good to keep that in mind. It'll pop up when we have other kinds of shapes. All right. Yeah. So at this point, we need to be defining a couple of things. All right. This shape is a cylinder that is, or it's a line made up of tiny little charges. And so what we have here is a linear density of charge, a uniform linear density of charge. And we represent that with this right here, the total charge based on the total length, okay, charge per length. But for our scenario here, we have a dQ. So we're going to call this dQ over dl. Now you'll see that I'm going to replace that dl, or I'll replace it now with a dx, because this is the total, or how much the length of the cylinder is changing. Now I'm going to rearrange the density of charge in a way so that you can see exactly what we're going to be able to use. Because if you take a look at the formula over here, we see everything is in terms of dq. So we see that dq, this should be a lowercase q. This dq is equal to lambda dx. All right, so that is something that we can use. Now, you might be wondering, Mr. Lee, why are we doing it this way, right? So why do we define the linear density of charge, and why are we creating more tiny bits of things? Well, the reason is we have to make sense of what's going on here. We're adding up tiny bits of charges, but when we're adding up the tiny bits of charges, we're increasing in length. So as we add each tiny bit of charge, we are building up this cylinder, and this cylinder has a physical bound of its length. And so when we are doing the integral, we're integrating it from the leftmost charge, which is at point A, to the rightmost charge, which in our coordinate plane, this is what we can call A plus L. So we have the E field, and our bounds, our lower bounds is A, and our upper bounds is A plus L. All right, so we have this defined, and if we put this in as K dQ over R squared, we run into a little problem. So for those of you that are pretty savvy with calculus, you're thinking, we can't integrate this, right? Because if we try to integrate this, if you take a look at our tiny bits of things, our tiny bits of things here is a tiny bit of charge, dq, but our bounds are a unit of measurement of length. So we can't integrate tiny bits of charge when our bounds are with units of length. And that, my friends, is where this comes in. So what we're going to do here is a quick little substitution. So we have the E field is equal to the lower bounds of A and upper bounds of A plus L. I'm going to substitute in that dq, so we get the k. I'll show you my substitution by leaving in parentheses k lambda dx over r squared, but I want to keep everything with the same variable. So instead of calling it r squared, let's call it x squared, like so. Okay, if you want to leave it as r squared, that's fine, but just know that your r and your x, it represents the radial position. All right, now at this point, all the rules of calculus are set in place, and all we have to do is actually do the integral. So I don't want to skip any steps, so I'm going to do this step by step. I'm going to pull out all my constants first. So I'm going to highlight my constants in yellow. I have k here, and I have lambda here. Those are my constants. I pull them out. K lambda, I have my bounds, a lower bound, a plus l upper bound, that's my length, and we have 1 over x squared dx. All right, and at this point, all we got to do is integrate 1 over x squared, and we should get k lambda to the x to the negative 1/2 power with our bounds a and a plus l. All right. Now, at this point, we can plug in our bounds, and we would get k lambda a plus l minus k lambda over a. Now, at this point, I encourage you to not leave it in this form for the sole reason of really cool things start to happen when you actually combine these terms. And so I'm going to create a common denominator. We're going to do k lambda a minus k lambda times a plus l all over a plus l parentheses times a. All right. Now here we're going to use a little bit of math magic, and we're going to see how certain things get canceled out. So here we see k lambda a, and here we see k lambda with the minus sign, and here's the a. So if we distribute this k lambda and this a, okay, that's a negative version of the first part that we highlighted. So the two will cancel out, leaving us with only negative k lambda l all over a plus l parentheses a. And this is our final answer, and that negative simply means that we have something going to the left right there. All right. Now, what we can do at this point, because we don't want this charge density there for the sake of the next couple of seconds about what I want to explain. So I want to replace that lambda L with Q. Okay, as a reminder, lambda is charge per length. Okay, so I'm going to replace lambda L. Once again, I'll highlight it so you can see exactly what I'm substituting, okay, with my Q. So we get an E field, which is equal to negative KQ over A plus L parentheses A. All right, and that is my E field. If we were to take a look at the E field from the left-hand side of the rod. All right, so I kept on saying, like, it's important for us to not have that giant term, but to truncate it down, because you might see a question like the following. Okay, if A becomes much greater than L, what happens? So what this means is that, remember, A is the distance that the rod is from the origin. So right now, if this is our little drawing, and this is our rod, okay, our rod's length L and the distance A, okay, L is, a comparable size to A. But what this is saying is that if our distance is so far away that our rod basically looks like a tiny little speck, okay? So when this distance A is so big, that our rod becomes a tiny little speck, what happens? Now, mathematically, this is where we can do a little bit of hand waving, and our prowess in math really shows off. When this happens, we can say L basically approaches a numerical value of 0. It simply doesn't exist. Now, from a conceptual point of view, okay, we still have a rod there, but if we take a look at it, this cylinder essentially becomes a point charge. And we know what the formula for a point charge is. Okay, we started off this entire video with that. So if we have a formula of E is equal to negative KQ, A plus L parentheses A, okay, and we set all of our L's to 0, we end up with negative KQ over A times A, which is just A squared. And this, my friends, looks just like the formula for the E field of a point charge. Wasn't that cool? All right, so a quick little recap. In order to be able to solve these kinds of formulas, one, you have to ask yourself, will Gauss's law work? And the answer is no. You have to go through this calculus version of finding the E field. Okay. Number two, make sure you set up the E field formula accordingly. Okay. Make sure that you know what is the tiny little bits that you are changing. Set your bounds accordingly, and make sure whatever you're integrating to your bounds matches up to the variable that you're taking tiny bits of amounts to. And usually that conversion comes with your densities. Now, if you're not given a density, you might be given a function. Okay, make sure you use that function, and we'll get that practice in class. And after that point, it is just calculus. You do some integration and come up with a final answer. Now, it's important because Efield does have direction. You include that in your final answer. So our final answer of the Efield is pointing to the left. And that will come back into play at later videos where we have to take a look into the symmetry of the E-fields. And those symmetries will actually be very helpful for us. All right. And the very last thing that we did is we looked at a new concept of very, very, very large distances. Okay, if you see something like this on a problem, just so you know, essentially what they're saying is if one number becomes so big, the other number becomes 0. Okay, and they want you to know, he said, what happens when this is the scenario. All right, that's it. I'll see you next time. Bye bye.